you want to, you can ask me.
Welcome guys to today's class. In today's video, we want to discuss another important experiment in physics practical, and that is experiment on cantilever. This experiment is related to that experiment in bending moment. Experiment on bending moment is related to experiment on cantilever. That means as we embark on this experiment, you will see that it applies the principle of bending, the principle of depression. Okay, so it's important to note that this experiment will be of two types: the one involving the use of principle of bending or depression, and the one that make use of what? Oscillations. Okay. It has the objective to determine the Young modulus of a meter rule. The meter rule we talk about is that 100 centimeter rule, the one you make use of in the lab. Apparatus are 2 meter rules, G clamp, rotor stand, sets of weights, a vernier caliper, and a pointer. That means we need 2 meter rule to embark on this experiment. Now look at the diagram. Okay, use a G clamp to clamp a meter rule. You take one of the meter rule, clamp it with G clamp. Look at the G clamp clamping it, such that about 75 cl of the meter rule is projected. Wow, that means here is 0. So from here to here will be 75 cm. That means about 25 cm will be inside here. About 25 cm will be from here to here. Okay, so from here to here will be 75 cm. Okay, measure the distance of the meter rule above the ground using the second meter rule and record this value as PO. Now you keep another meter rule, the second one, vertically. This start from 0. You measure this distance from 0 to what? To this point. Measure the height of this meter rule from the ground. Call it your PO. Okay? When you call it your PO, then hang a mass M equals to 100 gram at 5 cm mark from the free end of the meter rule. Look at the free end of the meter rule. So calculate 0.5 cm and put your what? Mass on it. Put your mass on it. Calculate from here to here is 5 cm. Put your mass on it. So when you put the mass on it, something will happen. That mass, it has weight, and so it will try to what? Depress or bend the meter rule. That is where the principle of bending or principle of depression comes in. If you get a higher Young modulus, it means that that meter rule is very stiff. So the Young modulus have a direct relationship with how stiff and how flexible a meter rule is. Look at what I am saying. Look at a meter rule. If I insert a mass on this meter rule, if this meter rule is very stiff, the way it will bend will not be the same with the way the one that is flexible will bend. I don't know if you are getting what I'm saying. There is an amount of mass I will keep on this meter rule, it will break it if it is very stiff. But if it is very flexible, there is, whenever I put mass here, it will just be bending like broom, like flexible broom. Are you getting it? It will just be bending like flexible broom, so to speak. So, and when you remove the mass, it will go up. Are you getting it? But when you are dealing with stiff meter rule, when you try to bend it, it can break. Are you getting it? So how stiff a meter rule is dependent on what? Value of Young modulus. So Young modulus is a way of determining quantitatively how stiff or flexible a meter rule or any instrument, so to speak, is. So the higher the stiffness, the higher the Young modulus, so to speak. Okay, and so we are applying this principle of bending to see how flexible, how stiff the meter rule is. And so from what we will get, we will be able to check our answer. So this experiment, applying the principle of bending is this. Then applying the principle of oscillation means that this meter rule will what? Keep it to oscillate. It will just be moving up and down. Are you getting it? So it depends on how you stretch it. If you stretch it too high, it will move as fast as possible. If you stretch it small, at a small angle, it will be moving small, so that you will not you will not make mistake. But while trying to pause your stopwatch, you pause it below the time or above the time or above the number of oscillation given. So that is one. So when we hang equals to 100 gram, this will depress or bend. We take the watts distance from the ground to it. We call it our P. Then we subtract PO and P to get our Y. That is how to perform it live and direct in the laboratory. Then record the difference between PO and P. I've talked about it. When you record the difference, you call it your Y. Then repeat this experiment with masses 200 gram, 300 gram, 400 gram, 500 gram, and tabulate your readings. Yes. Now, the essence of this experiment I'm performing here is for us to see how we can perform this without stressing ourselves, setting up apparatus. So the only thing I will need in this experiment is to measure from 0 to what? To the PO, to note my PO. Once I note my PO, the whole thing is sorted out. I can continue what I'm to do. Okay, measure the breadth, the thickness of the meter using vernier caliper. Wow, we have to use a vernier caliper to measure the breadth. Breadth means from here to here, and the thickness means from up to down. That's how thick the meter is. Now that is about the first one. So we'll see how to do the manipulation without wasting our time. We'll get your answer. Set up the experiment again. We want to see another experiment. This time, set the mass M equal to 100 gram into oscillation. When you put the mass M, you what? When I put the mass M here, are you getting it? The emitter is clamped. I put the mass M. So what I will now do is that I will keep it to be in oscillation. It will be counting. I'll be counting 1, 2, 3, 4, 5, 6, and keep my stopwatch. Are you getting it? So I am to get for 10 complete oscillations. Yes, when I get to the number 10 oscillation, I stop. So getting to 9, I'm about to stop. Record the time T of the oscillation. Repeat this experiment for M 200, 300. So for 200, when you immerse it, you set it on it oscillation again. Please ensure that you don't stretch it too much. If you stretch it too much, it will move as fast as possible, and you may not be able to get your 10 oscillation accurately. So stretch is very small, at a very small, and that means this is one of the precautions you have to say, that care was taken while stretching or bending the meter rule by ensuring I bend it at a very small angle to minimize error. Are you getting it? So when you say what you did, try to tell them how you did it and why you did it. Care was taken while bending the meter rule by ensuring that it is bent at a very small angle so as to minimize error. Okay, that is one of the precautions you will say or you write in this experiment. Repeat this experiment for this. Okay. So after we do this experiment, we plot a graph of M against Y and obtain its slope. Plot a graph of M against T square and obtain its slope. Deduce the value of Young modulus of A from the two graphs. Yes. So that is what we are told. Okay. Now to see how to fill this table, first thing you have to do is note your PO. Take the measurement of distance from the ground to the height of the meter rule that you clamp on the desk. Note it. So we noted it to be 86 cm, which is equal to 0.86 meter. Cm divided by 100 will give it to you in meter. Remember, we said this experiment tells you how stiff or how flexible that meter rule is, both from the principle of oscillation and from the principle of depression. That is what this experiment will help us to appreciate. Okay, now we have noted our PO and we have our mass. So I've tried to convert the mass to kilogram. It was given in grams, and grams divided by 1000 gives you kilogram. Okay, so I will write 0.86. 0.86 is constant. Your PO is constant. Okay, remember I said once you note your PO, you don't need to perform any other thing anymore. Once you note your PO, you are covered. Okay, we come again. We now say that how do we get this our y? This our y has a formula that y is equals to k times m, where k is a constant, m mean masses. These masses we talk about. Then what is the value of k? What is the meaning of k? K means GL cube. K means GL cube BT cube E. Now, what do we mean by this E? E denotes the Young modulus we are talking about. Young modulus we are talking about. That is this E. Are you getting it? Young modulus. And so, for meter rules, for most meter rules we have experimented on, the Young modulus falls between 0.33 to 3.31 times 10 raised to the power of 9 Newton meter squared. That is what the range is, depending on how stiff. That means anyone about 0.3 is more of flexible, anyone about 3 points is more of what? Stiff. Are you getting? The higher the Young modulus, the more stiff the meter rule is. Now, this is about Newton per meter square. Someone can say, let him put it in dyne per centimeter square. That means we can put it in many units. And so these are some of the units we can put it to be. And so, what is the relationship between Newton meter square and dyne? Tell them that 1 Newton meter square is equal to 10 dyne per centimeter squared. 1 Newton per meter square equal to 10 dyne per centimeter square. And so here will be 3.3 to what? 33.1 times 10 raised to the power of 9 dyne per centimeter square. Okay? And so we are to I want us to use Newton per meter square because I'm putting every of my units to be in SI units. Okay? And so we say, let's take our what? Modulus to be 0.5. Take the modulus of the meter rule to be 0.5 because the ones I have experimented on, majority of them have been giving me 0.5. And so let's just take it to be 0.5. And so we now say this K will be equals to G is what? 9.8 meter per second squared. L is equal to 0.75 meter. E, we have noted it. Now the breadth of the meter rule I use the vernier caliper and measure from here to here. From here to here. That means distance from here to here. The breadth gave me 2.5 centimeter, which is equivalent to 0.025 meter. Then I also use the vernier caliper to check the what? The thickness. Are you getting the thickness of that meter rule? And it gave me that the thickness is equal to 0.5 centimeter, which is equivalent to 0.005 what meter. Because when you divide centimeter by 100, you get it in meter. So getting our care, we say 9.8 times 0.75 all raised to the power of 3 all over 4 times 0.025 times 0.005 all raised to the power of 3 times 0.5 times 10 raised to the power of 9. Okay. Okay. So what you now do is that you use your calculator and start packaging all you have here. You start to tell them that 9.8 times 0.75 cube divided by bracket 4 times 0.025 times 0.005 cube times 0.5 times 10 raised to the power of 9. So that will be giving you equal to 0.6615 meters. 0.6615 meters. Are you getting it? That means our y, since k is 0.6615 meters, our y will be equal to k times the mass. So watch how we do it. The first mass is 0.1. 0.1 times this, that will be giving you 0.1 times 0.6615. That will be giving you 0.06615. Please try to use your calculator and follow me through, okay? 0.06615. I've noted it. Then what I will do is that I'll approximate it to be 0.07 to 2 decimal place. I will go again 0.6615 times 0.2. That is the second mass. The second mass is 0.2. That will be giving me 0.1323. Approximated to be what? 0.13. Then we say times 0.3. That will be giving me 0.19845. Approximated to what? 0.20. Then times 0.4. 0.2646. That is approximated to 0.26. Then times 0.5. That will be 0.33075. 0.33075. That is approximated to 0.33. So we have gotten our y. That means if I am you, once I just get the height, I'll just go home and use my calculator within 2-3 minutes, get my what results, depending on how fast you are in pressing calculator. Getting your P. Since we noted that PO minus P is equal to Y. Since we noted that PO minus P equal to Y from the diagram, that means that P will be equal to PO minus Y. So we be subtracting. We'll be saying 0.86 minus 0.07. What will it be giving you? 0.79. 0.86 minus 0.13. That will be giving you 0.73. 0.86 minus 0.20. That will be giving you 0.66. 0.86 minus 0.26. That will be giving me 0.60. 0.86 minus 0.33. That will be giving me 0.53. So we have gotten the full table for the first experiment. If you enjoyed this video, please don't forget to click what? Like, subscribe, share to your friends. That subscription is very important to me, okay? That is a way of promoting my channel, showing me you appreciate my good work. Yes, share to your friends so that they too can learn as well. Then we go to the second experiment. They say set up the experiment again. This time set the mass M equal to 100 gram, 200 gram, 300 gram, 400 gram, 500 gram into oscillation to perform simple harmonic motion for 10 seconds and for 10 complete oscillations, and record the time t of the oscillations. Now we have noted our PO, our P, so we don't need to take measurement of any other thing. What we have to do is we tell them that again T square is equal to K M again. How? In this case, what is value of K? The value of K, where your K is equal to 16 pi square L what? Cube all over BT cube what? E. Tell them that K is equal to 16 pi square L cube all over BT cube what? E. We know our E. Our E is 0.5 exponential 9 Newton per meter squared. Okay? And so, we know our L, we know our B, we know our thickness and our E. So we say our K will be equal to 16 pi squared times 0.75 cube all over 0.025 times 0.005 raised to the power of 3 times 0.5 times 10 raised to the power of 9. So we press it in our calculator. 16 pi squared times 0.75 cube, then divided by bracket 0.025 times 0.005 cube times 0.5 times 10 raised to the power of 9. So you'll be getting 42.63669101, and that will be giving you 42.64. That will be giving you 42.64 42.64 second square over what? Kg. That first one we got, we said that the K is equal to 0.6615, right? We said that K equals to 0.6615. Please, the unit of that first one, because we are talking about Y equals to K M, the unit of that first one is equal to meter per kg. Please, very important that you take note of units. I forgot it. Please don't make that mistake I just made now. Don't forget to include your unit. Your K 0.6615 meter per kg. But this one K is what? 42.64 second square over kg. So note it. So the first value of t square, will be equals to this times 0.1. 42.64 times 0.1. And when you multiply this, it will be giving you 0.4264. So we'll be having it will be giving you 4.264. Then we'll be having it to be 4.26. That means 42.64 times 0.1. 4.264 approximated to be 4.6. Please, we don't put it here. You put it to where it belongs. 4.2 watts. That is about t squared. So we now said this same figure times 0.2. 42.64 times 0.2. That will be giving me 8.528. That is 8.53. So we also say times 3. 42.64 times 0.3. 12.79. Then times 0.4. That will be 17.06. Then times 0.5. That will be giving you 21.32. Okay? So we have gotten your t square. T square is related to this t by square root. So when you get the square root of t square, you get your t. Oh yeah. Square root of 4.26 will give you what? 2.06. Square root of 8.53 will give you what? 2.93. 2.92, please. It's a mistake from me. Square root of 12.79. That will be giving you 3.58. 3.58, right? Then square root of 17.06. That will be giving you 4.13. Square root of 21.32. That will be giving you 4.62. Okay? Yes. Now we go to our t. How do we get our t? Remember that your period is equal to time it takes to complete what? The given number of oscillation or cycle. And so the time given is what we have to look for. It implies that t is equal to n times t, where n is 10. 10 complete oscillation times each of these t you have. So 10 times 2.06 will be giving you 20.60. 10 times this will be giving you 29.20. 10 times this will be giving you 35.80. 10 times this will be giving you 41.30. 10 times this will be giving you 46.20. Wow. We have successfully produced our table. Okay? Yes, we have successfully produced our table. We will go to graph plotting now. Now, this is a sketch of a graph. So this is not the actual standard graph you know. It's just a sketch. Now, we want to use this sketch and learn a lot of things in graph plotting of this experiment. So first thing you have to do is write the date. I always say it in all the videos I've been talking about. Write the title. A graph of what are you plotting? A graph of M in kg against Y in meter. Please write the title. Now, next is choose appropriate scale. We have posted videos, a lot of videos on how to choose appropriate scale. So do well to click on our YouTube, Chidon's Daniel, how to choose appropriate scale. Click Chidon's Daniel, how to choose appropriate scale. You see plenty videos we have posted there on how to get error in slope, in intercept, all of them you will see them there. So do well to what? Click it. Okay. Then next thing we are to do is we now say, how do we choose our what? We label our Cartesian axis. We call here our M in kg and our what? Y in meters. Now we have 1, 2, 3, 4, 5, 6, 7. If we say 0 here, 0.1, 0.2, 0.3, 0.4, 0.5. Wow. And the highest we have here is 0.5 for M. So we can say, should we plot from 0 from origin? Is left for us because it was not instructed. Okay, let's check this too. Should we start from origin here too? Let's check. So if I say 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 6 will be giving me 54. Oh wow. 9 times 3, 27. So 9 times 4, 36. We can go by 0.04. You just say, if I start 0.0 here, if I wish to start 0.0 here will be 0.10, 0.20, 0.30, 0.40, 0.50. So the idea of choosing appropriate scale is to choose a number that will accommodate in the graph, such that the difference between each of them will be giving you the same thing. Are you getting it? And so come to this side, we'll be choosing 0.04, 0.08, 0.12, 0.16, 0.2, 0.24, 0.28, 0.32. Okay. 0.08, 0.16, 0.12, 0.16, 0.20, 0.24, 0.28, 0.32, and 0.36. The highest is 0.33. So we have choose our appropriate scale now so that it will balance. We plot 0.1 against 0.7. 0.7 will be close to 0.8. We put. So use your standard graph sheet and see that you trace it well and plot it, okay? 0.2 against 0.13. Look at 0.12, so 0.13 will be here. Then 0.3 against 0.2, that one is perfect. 0.4 against 0.26. This is 2.4. So 2.6 will be in between. 0.5 against 0.33. This is 0.32. So 0.32 will be somewhere here. So we have located our points. Next is to draw our line of best fit. Okay, we have located our line of best fit as you can see on this graph. Now, next is to get our slope. To get our slope, we draw our vertical line. So, we are drawing our vertical line, then and our horizontal line. So, we say change in M equals to, this point is about 0.49 minus this point is 0.10. This point is change in Y equals to 0.32 minus this is 0. Let's say 0. What 06. 0 since here is 0.07, so 0.06. Then we use our calculator and say our slope is equals to change in M all over change in Y is equals to 0.49 minus 0.10 all over 0.32 minus 0.06. Okay, let's check. Equals to 0.39 all over 0.26. That will be giving us 0.39 divided by 0.26. 1.5. Vertical is kilogram, horizontal is meter. Now, because they say we are to do the one of 2, but because they say deduce the value of Young modulus E from the two graphs. So from this graph, our Young modulus, since we said that Y is equals to Km, making M subject of formula, we have that M is equals to what? Y times inverse of what? K. Y times inverse of what? K. Where you are plotting the graph of M against Y. When you plot the graph of M against Y, 1 over K will be the slope and it's passing through the origin. Let's check it. Y times 1 over K simply means 1 over K bracket Y. And so we have to clean everything and package it well and say equals to 1 over Y, 1 over K. Are you getting it? We have it this way, where the slope will be inverse of what? K. Your slope, which is K, whatever is your slope will be inverse of K. Okay, now we said that K is equals to GL cube M GL cube all over 4 BT cube E all over 4B cube E. Now from here we said Y is equals to Km and K is this. That means Y will now be equals to what? Y is equals to this times what? M. Are you getting it? We make E subject of formula. We make M subject of formula. M will be equals to M equals to 4BT cube what? E Y all over what? G G L cube. We have it this way. That means when you plot the graph of M against what? Y. This becomes your slope. This becomes your slope. Are you getting it? This will be your slope. And that your slope is equals to 1 over k. That your slope is equals to 1 over k. 1 over k. So what is our slope? Our slope is 1.5. We say 4b t cube e all over gl cube is equals to 1.5. Because the slope, which is 1 over k, is gotten to be 1.5. We make our e subject of formula. Making our e subject of formula, we have that e will be equals to, this times is 1.5 gl cube all over 4b t cube all over 4b t cube. So when you compute this, whatever it gives you becomes your answer. Let's compute it. We said 1.5 times 9.8 times 0.75 raised to the power of 3 equals to this, divided by bracket 4 times, what is our b? 0.025 times 0.005 raised to the power of 3. So that will be giving you 496,125,000. We tell them that our E for this is equals to 496,125,000. That means Newton per watt meter square. 1, 2, 3, 4, 5, 6, 7, 8, 9. 496,125,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That means equivalent to 0.496, or if you know that when you approximate it now to one decimal place, what will it will give you is 0.50, right? 0.50 times what? 10 raised to the power of 9 Newton per meter square. That is the value of A you have gotten. That means from principle of bending or depression, you can get the E of a meter rule. You can get the E of a meter rule. Remember, 1.5 is our slope times G, 9.8 times L, which you say is 0.75, times B, all over 4B. B is 0.025, T is 0.05, then T is 0.005, please. T equal to 0.005, B equal to 0.025, etc. And so you cube it, then you get your answer. We want to plot the second graph now. That is a graph of M against T square and obtain E slope. We say here, the date, you write your date, we'll name the title a graph of what? M in kg against T square, a second squared. So once you have labeled it, we are plotting M now against T square. Now we can say let us start from the origin for Y. Let's start from the origin for Y. This is your Y. 0.10, 0.20, 0.30, 0.40, 0.50. Now label your Cartesian axis appropriately. This is mass in kg, while this is T square in second squared. Are you getting it? Then for your X, as is. If we say let's use 2 now, for instance, to watch how we are taking this scale, watch it on our channel, Chidon's Daniel, how to choose appropriate scale, so that you see the manipulations that are being done there, how to get it sharp sharp. But at this point, I'm not going to be doing such thing often and often. So over and over again, so I just want to do it as fast as possible now. We have t square 4.26, 8.53, 12.79, 17.06, 21.3. If I go by 2, 2, 4, 6, 8, 10, 12, 40, it can go. Then I can say let me go by 4. 4, 8, 12, 16, 20, 24. It will go. So 4, 4.0, 8.0, 8.0, 12.0, 16.0, 20.0, 24.0. So the scale you use depends on the standard graph you are using and how many big bars you can see there. This is just a sketch of the graph. Are you getting it? So you use your own to see what it will give you. That means we are starting from 0 2 for the x. This is for x and this is for y. Okay? Then 0.1 against 4.26. Wow. Against 4.26. Look at 4. 4. Look at 8. 8 minus 4 will give you 4 divided by 10, 0.4. So if we have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4 over 10, 0.4, right? 4.4. 4.4 will be the next, but here is 4.26. So we now say it will be here. Then 8.5. 8.5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8.5. The next one should be 8.4. So 8.4. But what we need is 8.5. We'll take it like this. Then what else? 0.3 against 12.8. 12.8 should be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 12.4, 12.8, we can get it. Then we take again 17.06 against 0.4. 17. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. 16.4, 16.8, 17.2. So like this. So 17.2, it should be less than 17.2 because what we can get is 17.2, not 17.06. 21.32, 21.32. This is 20. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 20, 20.4, 20.8, 21.2, 21.6. So around here. Okay. So we are finished sketching the points. Now let's draw our line of best fit. Okay. Wow, we have drawn our line of best fit now. We can see only one fell out. So what we have to do now is we get our slope. Let's get our slope. Okay, so it starts from here, end here, then end here. So we say here is change in M, change in m is 0.55 minus 0.1. Then here is change in what? T square equals to, change in t square is equals to 24 minus 4.0. So we say slope equals to change in m over change in t squared. What is change in m? This minus this, 0.45, all over this minus this is what? 20. What will it be giving us? We'll be having 0.45 divided by 20 equals to 0.0225. 225. What is the unit? Kilogram per what? Second squared. So that is the slope. That is the slope we get from this graph. But they say also deduce the value of your modulus A from this second graph as well. Okay, to deduce it, recall that we said that t square is equal to km. That means making m subject to formula, m equals to 1 over what? K times t squared. Times t squared. That means what is our k? We say our k is equal to 16 pi square L cube all over b t cube what? E. All over this. And when we finish plotting this, that means what is k now? What is our slope? We say this is our slope, but k is 16 pi square L cube all over bt cube E. Since t square is this, what will be your t square? T square will be equals to 16 pi square L cube all over bt cube E times what? M. Now making m subject to formula, this will go here. Making m subject to formula, this will go here. You now see that m will be equals to this times this bt cube what? E all over 16 pi what? Square L cube. So this times this is t squared. So when you have gotten this, it means that when you plot the graph of m against t square, this will be your slope. And what is our slope? 0.0225 is equals to bt cube E all over 16 pi square L cube. Are you getting it? Making E subject of formula, therefore E is equal to this times this 0.0225 times what? Times 16 pi square L cube all over bt cube. Okay, so let's get what our E will give us. We'll use our calculator. 0.0225 times 16 times shift pi squared times our L is 0.75. Is constant 0.75. 0.75 raised to the power of 3 divided by bracket. Our B is 0.025. Is constant. We got it using vernier caliper. Times our thickness is 0.005. 0.005 raised to power of 3. So when you compute it, you'll be having that your E is equals to 479,662,773.9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That means the unit is Newton per meter squared because we put everything in SI unit. Newton per meter squared. Yes. Now, approximately, our E will be equals to 0.5. 0.5 times 10 raised to the power of 9 Newton per meter squared. That means from these two experiments we just concluded, when you use the first approach to perform this experiment, the Young modulus you will be getting will be similar or nearly equal to the Young modulus you will get when you use principle of oscillation, principle of bending moment, principle of bending or depression, and the principle of oscillation. The Young modulus you will be getting from the two will be what? If not exactly the same, will be similar or nearly equal to. Okay, so that means there are many ways you can get Young modulus using of bending moment principle, cantilever, that is using principle of depression as well, and using principle of oscillation. You can get Young modulus of that meter rule. Remember we said the lower the Young modulus, the lower the value of the Young modulus of that word meter rule, is telling you that that meter rule is flexible. The more flexible it will be. The higher the Young modulus, the more stiff it will be. So the higher, the more stiff, the lower, the more flexible. Okay? Yes. Please note it. Remember we said you can be asked to write precaution. If you are asked or if you are not asked, please include your precaution. And we mentioned one of it, that the that care must be taken to see that this why depressing this meter rule, that you depress it at what? At a small angle. Are you getting it? You depress it at a small angle so that to minimize error, because when you depress it at a small angle, are you getting it? When you depress it at a small angle, it will be rotating slower, and so you can count your 10 oscillation. But when you displace it at a higher angle, you see it moving fast, oscillating fastly, and so you may find it difficult to get the actual oscillation given to you. Maybe by the time you're about to pause your stopwatch, it has even reached 15 oscillations, or it has not reached. So to be on a safer side, displace it at a very small angle. If you find this video very interesting, please don't forget to like the video, click subscribe, share to your friends, comment. Yes, comment. Tell me your opinions, tell me your challenges on the comment box so that we interact together. Thank you once again for believing in my service.